another definition. So two vectors A and B are called orthogonal if the angle between them is pi over 2, i.e. 90 degrees. So in other words, they're perpendicular. And we can write A, and this sort of upside down T, B. We read that as A perp B. And here's the fact. A is perpendicular, orthogonal, whatever, to B, precisely when A dot B is equal to 0. This follows immediately from A dot B equal to magnitude of A times magnitude of B times cosine of theta. Really, we're assuming that A and B are non-zero vectors. The zero vector is perpendicular to everybody we just pretty much considered. So, if this is 0, neither of these is 0, if they're not the zero vector, so this has got to be 0. And this is 0 precisely when pi over 2 is, the angle is pi over 2. So there you go. That's where this comes from. So this is really one of the most important ways that we can use the dot product. Recall from Calc 1 that we're really interested in tangent lines, and sort of the generalization for us in Calc 3 are tangent planes and other sorts of tangent hypersurfaces, whatever that might mean. But it turns out that we're often also interested in something called a normal vector, and a normal vector is going to be perpendicular to the tangent plane, and this is going to be really important for us. It's something that didn't appear so much in Calc 1, but Calc 3, super important. This helps us deal with that. Okay, so let's do an example. Let's see which of the following pairs of vectors are orthogonal. Let's try each pair of vectors. So first, u dot v. U dot v is equal to 3 times negative 1 plus 2 times 1 plus negative 1 times 2, which is negative 3 plus 2 minus 2. So that's negative 3 plus 2 minus 2, which is equal to negative 3. So note, they are not orthogonal. How about u dot w? That's 3 times 1 plus 2 times negative 1 plus negative 1 times 1. This gives us 3 minus 2 minus 1, yes. Great. So those are orthogonal. And finally, v dot w is negative 1 dot 1 plus 1 dot negative 1 plus 2 times 1. This is negative 1 minus 1 plus 2. That's also 0, so yes. So we have that u is perpendicular to w, v is orthogonal to w. Orthogonal, perpendicular means same thing. But u and v are not orthogonal to each other. So if we fix a vector and look at the standard basis vectors I, j, and k, we get 3 very important angles called the direction angles of A. And we tend to call them alpha, beta, and gamma, the first 3 letters of the Greek alphabet. So here we have some vector A, which is this blue vector right here. Alpha is the angle that it makes with the positive x-axis. Beta is the angle that A makes with the positive y-axis. And gamma is the angle that it makes with the positive z-axis. And the dot product, because it gives us the angles between any two vectors, will immediately give us these angles when we take the dot product of A with the standard basis vector. So let me run through the argument for the standard basis vector I, which is the vector in the x direction. So cosine of alpha, well, alpha is supposed to be the angle between A and the positive x-axis. But we have this formula for the cosine of an angle between two vectors, which is the cosine of the angle between two vectors is their dot product divided by the product of their magnitudes. And since I goes in the direction of the positive x-axis, we get cosine of alpha is A dot I divided by the magnitude of A times the magnitude of I. Now I is 1 in the x component and 0 in the other two. So when you take the dot product of A and I, A1 times 1 gives us A1, and the other two components of I are 0, so A2 and A3 from A go away. If you need to, write that down, convince yourself that's true. Also, I is a quote-unquote unit vector. Its magnitude is 1. Again, its components are 1, 0, 0, so 1 squared plus 0 squared plus 0 squared is 1. Square root of 1 is 1, so its magnitude is 1. At the end of the day, cosine of alpha is A1 divided by the magnitude of A. Similarly, cosine of beta, the angle that A makes with the positive y-axis, is A2 divided by the magnitude of A, and cosine of gamma is A3 divided by the magnitude of A. So these direction angles actually give us something nice in terms about the vector A. Now here's another definition. A unit vector is a vector of magnitude 1. Given any vector A, we can always find a unit vector in the same degree, in the same direction. We just have to scale it down or up until we get a vector of magnitude 1. In fact, if we take A and divide it by its own magnitude, then we get a unit vector in the direction of A. And first of all, that it's in the same direction of A follows from the fact that we're just dividing by a positive scalar. Second, to show that the magnitude is equal to 1, just find the magnitude of this vector, which is A1, which has components A1 over the magnitude of A, A2 over the magnitude of A, A3 over the magnitude of A. So just square each component, add them up, and see what you get. Okay. But this last expression actually shows that the unit vector in the direction of A, which is A divided by the magnitude of A, is equal to cosine of alpha, we just showed that, cosine of beta, cosine of gamma. So these direction angles also give us an expression for the unit vector in the same direction as A. Alright, so this question just popped into my head, question number 3. What are alpha, beta, and gamma for the vector with components 1, 1, 1? I don't know what the answer is, I'm just curious, so go ahead, do it.